Okay. Oh, good. I'm glad we didn't get that on the recording. All right. Good morning, everybody. Hope you had a good night, good day, good afternoon, and we're ready to get back to work. And I will stop sharing my screen. Thank you for playing with that. Here is, so I'm going to stop sharing my screen. Here's our schedule for today. Today you're going to spend most of the time working either in one sort of breakout room or another. And so here's my schedule. So some of you wanted to know a little more detail about what you were doing today. And actually, before I do that, let me just ask. I'll try and escape out of this. Nope, I can't escape out of this. I'm going to share and then stop sharing. Did anybody not get a chance or not have an opportunity to organize yourself in your group, in your time zone groups, and review some of the materials that we had yesterday, those of you who are here? All right, so everybody had a chance to look over the materials from the event. Great.
Are
Okay.
you taking silence as everybody's able to do it?
I'm taking silence as everybody was able to do it. Yes, since that was okay. I asked it in the negative rather than the positive. So, which of course is like nobody wants to admit that they didn't do the assignment. You all did the assignment, right?
Yeah.
Well,
nobody's
okay.
Claiming
well, you'll have an
Starbucks.
Opportunity.
Nobody's
yes.
claiming the Starbucks gift card that we wrote in. Put a thumbs up when we start and you get it. But oh well.
I thought it was scotch. For those of you who are just joining us, if you could make a point of logging on about 5 minutes early, that would be great, so that we can get started on time regularly. All right. So here is my plan for today. Many of you were asking what the plan was, and I didn't want to tell you because I hadn't quite created it yet. And so, but there was a plan. And here is, I've now created it and written it out. So we're going to start this way. What you've already seen what the sort of the overview of the activity. If you like scan through the whole document that I shared with you, that there's 4 different domains that we typically break solar physics up into. Now, part of Carl's message from yesterday is there's a lot of things that cross over. There's a lot of processes and a lot of physics that crosses over those domains. So, but at the same time, there's also a lot of specialization and methodologies that are special to those domains. Data interpretation, and models that are specialized to those domains because of the unique physics in each of those domains. So it's valuable to become an expert in, as you all are doing in your graduate career, become an expert in a particular field while still keeping an eye on the big picture and recognizing where you can cross over and where you can make contributions across different domains. So the data set for the event that I'd like you to go through is broken up into those 4 domains: solar, wind, magnetosphere, and ionosphere. And in part, this exercise is a little bit of a throw you into the pool and see who is foundering and go fish them out and help them and then try it again. Oh, somebody's got a, okay. So so it's not meant to get the right answer right away. It's meant to practice with some things. Thank you, Pauline, for posting notes. Anybody else from the time zone groups that want to post notes should post them now. That would be great. So here's the plan. You're going to spend 5 minutes in your synchronous groups. Ultimately, you're going to come back into your synchronous groups at the end, and you're going to be putting this event back together. So, but before you do that, one member of each member of the group has to become an expert in what is happening in a particular domain. So for the first 5 minutes, all I want you to do is decide which member of your group is going to become an expert in each of the particular domains: solar, solar wind, magnetosphere, or ionosphere. You feel free, if you may have already become an expert last night as a part of your time zone groups, you can stick with that if you want. Or if you feel more comfortable with a different set of data or a different domain, you can decide, well, okay, I'm going to look at the data set for that domain rather than what I looked at last night. Right? But as a group, we need one person in each group in each of these domains. So typically the groups are 4 or 5. Of course, if you're 5, you're going to double up with somebody, so somebody gets to choose freely, as it were. But we need one person to be a domain expert. All right? So that's what you're doing in the first 5 minutes. We'll come back into the main room, and Maggie will set up 4 breakout rooms, one for each of the domains, and then you'll all go into those breakout rooms and spend about 45 minutes reviewing the data sets and models that were assigned to those domains. And then we'll take a break after that, come back, go back into your synchronous groups and put the jigsaw puzzle of this event together. All right. Questions as to what we're doing today? So that was the overview. Any issues, concerns?
Hi, Nick. Would you be able to post the list of synchronous groups?
I think we can do that. Maggie, do you have that handy, or do you want me to find it?
Nope, I can.
Great. You gonna drop it in chat?
Yes.
Great. Okay. Any other questions of what we're doing?
Lena's got a question in the chat.
Oh, yep. Thank you. So time groups. So we're starting, Lena, with synchronous groups. Then we're breaking into the so-called expert groups for the individual domains. So the time zone group work was just a warm-up. Is that good, Lena? Great. Okay. So double check which synchronous group you're in right now. And Maggie will open up the groups, and you got 5 minutes to sort yourselves out and have one person in each group pick one of the domains, and then we'll pull you back in 5 minutes, and then we'll put you back into expert groups. And if you've got questions, just yell for help. Okay. Oh, and so did you open up the rooms, Maggie? I guess
I did, yep. And people are joining.
Great. And do you have a timer, Maggie?
Yeah, I can start one. Absolutely.
I just want to keep track of 5 minutes and just
Yeah,
pull everybody back out after 5 minutes. And if we
great.
got any problems, we'll figure it out. All right, so 3, 3, 3.
And I think the default setting on Zoom is when you close a breakout room, it gives a 1 minute countdown. I think you can make that shorter, but
Whoa, there are way too many people in group 7. And I don't know. 1, 2, 3, 4, 5, 6. Oh, did I? Okay.
Keaton, Lena, Steven. I think that's everyone. Oh, no.
yeah, there's a few
I think there's
wrong group.
Yeah.
Looks like Pravita is in group 7 and shouldn't be.
Yes. Does anyone in here need any help figuring out what room they're going to?
I see Pauline's logged in twice, probably calling and
Daniel, do you know where you're going? I believe he's in group 2.
Yep.
I'm in group 2.
Yes, you're in group 2.
Okay, thank you.
Are you able to join that group?
Yeah, I can't join the group.
there should be a breakout room button at the bottom of your screen. And when you click on that, you can join group 2. You can just
What group is Pauline in?
yeah. I
So-
saw she had 2 sign-ins, then 3 sign-ins, and now 1 sign-in.
Yeah,
So it might be
and
a
she's
technical difficulty.
Oh,
she's
okay.
in group
Okay.
6.
Yeah.
She's joined twice in group 6 as well, or once in offline or something. So
Mhm.
it's the magic of multi-body Zoom. It's interesting. Some of these groups, when I'm looking at them, you know, they say they've got 4 people, but some of them are the same person twice.
Mhm. Yeah.
So I guess we're missing some people this morning because the groups aren't all quite populated as much as you would think.
Mhm.
Yeah, there's 31, including us, when we were breaking out. So we're missing a half dozen.
Yeah.
Okay. I'm gonna close all the rooms. Because with that 1 minute, that'll give us 5 minutes.
So this is one of the tests for passing this school is, can you follow my incoherent instructions? All right.
I had a high school biology teacher that we would have multiple daily quizzes every day, and it was essentially guess what I'm thinking. She would hold something up like a jawbone of a cow, and the right answer was adaptation. It's like, what? Okay, type of thing. So
Okay.
Throw
All
out
right.
random biology statements.
So raise your hand if you're going to the solar group. Yeah, so if you've got only 3 people, you're going to be missing an expert. I appreciate that. I don't quite know who I don't quite know what to do about that. We'll have to dock people on their permanent record for not showing up on the second day of the Heliophysics Summer School. So, all right, raise your hand if you're going to be part of the solar group.
and also, if you joined while everybody was away and not sure what is going on, you might want to, because I think there was 31 people.
There were 31, and now there's 38.
Yep. So we have some stragglers. So I think maybe that fourth person might be here. Okay.
Okay. So should we?
Well, let's see how it works.
Spend another, huh?
We could see how it works.
Hey, Nick.
Hey, what?
So my group was wildly confused what we were supposed to be doing, to be quite honest, because so we had 2 people that were in the solar corona / solar surface group yesterday.
Mm-hmm.
So we're trying to understand, like, are we supposed to do a different group? Like, what was the point of putting in all that work yesterday? I guess is my question. Are we supposed to investigate a completely different topic?
The point was to give you a little bit of a head start on what we're doing today.
Okay, so we can assign ourselves to something completely different that we're more comfortable with, maybe?
You can assign yourselves to something completely different that you're more comfortable with, yes.
Got it. Okay, thank you.
Is it worth going back, and now that we've got a full complement of people, is it worth going back into the synchronous groups for 2 minutes and making sure that we're sorted out?
And everybody knows what group they should be going into?
Well, I'm not sure. I mean,
yeah, Maggie, you might want to post that again, because as you don't get the chat and if you joined.
Okay, give me just a second. I already deleted those groups and had the other ones created.
Yeah, I'm sorry, Maggie.
That's okay.
Well, yeah. You don't need to assign people to the groups, just open up a group and they can just go in to where they're supposed to go.
All right, let's try this again. So now that we've got some clarification, and if you are confused, there should be a contact the host button on the bottom of your breakout room. Okay. So all right, are you going to reopen so here's the instruction. We're going back into the synchronous groups again. Incorporate anybody who came in late. And if you were confused about the first instruction, I think we've clarified it now. So each group needs 1 person to fit into each of the domains. Okay, so there's going to be 1 person doing solar, 1 person doing solar wind, 1 person doing magnetosphere, and 1 person doing ionosphere, independent of what you did last night. Okay.
All right, the rooms are open.
Great, thank you.
Yep.
If your group is good, stay in the main room.
So Nick, apparently Pauline's been having difficulties joining groups.
Yep.
And she keeps getting kicked out. I don't know what to do about that.
I'm not really sure either.
Yeah, I've had that happen. When you just try to leave the breakout group, it kicks you out instead of into the main room, but you can
You
just,
know what we didn't, check is to make sure everybody had an updated version of Zoom.
yeah.
Yeah. Well, I think this is actually a little different. It sounds like she's getting kicked out when she tries to join a breakout room, not
Yeah.
leave a breakout room. So
Yeah, I
I
think
know
it's
that
a
for me,
problem
when I
with
left the
my
breakout
operating
room,
system.
it gave me the option of either leaving the entire Zoom or just leaving the breakout.
Right.
So it's also possible people are picking the wrong button or something, but I don't know about joining if that's a problem. But
I think it's because I'm using Linux and for some reason it doesn't like Zoom.
yeah, that's been my, I know some other people who are Linux people and they've said various other things on Zoom really doesn't work. So
Yeah. Yeah, I don't know if there's much to be done about it. I just wanted to let you guys know if if I'm
Okay.
delayed
Yep.
going
Yeah.
back and
That's
forth.
fine.
Blaine,
I'm not
is it
skipping.
possible for you to join Zoom like via the web or something instead?
Yeah, maybe I should try that.
Yeah, sometimes it doesn't have all the bells and whistles sometimes, but sometimes it's a little more stable.
I'm gonna try that.
Nick, do you
Okay,
think it's
Maggie,
good to close them?
I think it's good to close them. Yeah.
Nick Perbita's got a question in the chat.
Oh, thank you. Well, okay, so we're gonna change now, Perbita. So you were in group 5, right? So now we're okay. How many people are in the solar group? Put your hand up. And there's a raise hand under the reactions. Okay, 1, 2, 3, 4, 5, 6, 7. I was hoping there'd be 9. How many people were in the solar group?
Suvik has his hand literally raised.
Literally up. Okay,
Yeah.
great. All right, so we'll go with 8, and we'll figure.
No, I think
see.
there's 9 now with Suvik.
Okay, great. Put your hands down, and so solar wind. Somebody's got their mic on with noise in the background. So we got 1, 2, 3, 4, 5, 6, 7. So looking for people in the solar wind group. Any groups missing a solar wind person? Was some okay. So I think 6. Keep your hands up if you're in the solar wind group. All right. 7. All right. So 2 groups seem to be missing a solar wind person. Is that right? Is there anybody speak up?
I'm not sure if Guang Lu indicated, but I think for our group 8, he's supposed to be our solar
Okay,
wind
that makes
delegate.
8. I'll go with that. Magnetosphere. So solar wind people, put your hands down. Magnetosphere. Okay, so that's 7. Any groups miss 8? Okay, great. We'll go with that. And then ionosphere. Okay, so magnetosphere people, put your hands down, and ionosphere. So that's 6, 7. Okay, any groups missing an ionosphere person?
Yes, group 3 is missing the ionosphere person.
Okay, great. Okay, and Frau Dese is indicating. So that means, all right. So
Group 1 also missing.
Okay, great. All right. So Maggie, I think is going to open up 4 rooms. One labeled solar, solar wind, magnetosphere, and ionosphere. And you should join one of those rooms. And for the next 45 minutes, so till about, let's give it till 10, let's call it 35 minutes, till 10:05, so 5 past the hour. Spend time either reviewing what you looked at last night or learning from the people who looked at stuff last night and looking at notes that are posted on the on Slack, and becoming an expert in that data set. All right, so go do that, and call for help if you need it, and I will be around to check on you in a little while.
And Andrea, is that a residual hand or a new hand for a question?
I'm sorry, it's a residual hand.
Okay, that's the problem. It's like, doesn't come down automatically. We should have the students publish a paper and put Starlink storm, you know, like a Halloween or Bastille Day, or
Well,
we have these Carrington storms. Now we have a Starlink storm. Or
claps are great. And got it. Okay, great. I think we're mostly back. Oh, come on. Here we go. All right. And so having, let's see. Let's, I'm not going to have each group review what they did, but what's one either question or challenge that the ionosphere group had? So somebody from the ionosphere group, what's a question or a challenge that you had while you were discussing the data that you were looking at? And I think Stephen was in that, and Sarah. Right? What's a question or a challenge that you guys had, or anybody else from that group?
I think one of the things we were curious about is we saw total electron content enhancements, but we weren't 100% sure what mechanisms were driving that enhancement, if I remember correctly.
Okay, great. Okay, great. Magnetosphere group. What's one question or challenge that you had?
Well, we saw
Well,
go ahead.
I was just going to say something that I'm confused about, and I think some of us are confused about, is there's no, like, I don't know, we kind of thought there would be something different in the GOES, like particle fluxes that would correspond with the solar wind activity that we see. And we do see activity in the magnetometer, but I don't know. I don't really understand how to read the particle fluxes, or not how to
Okay.
read it, but like what it means.
And I think those can be challenging. And which particle fluxes did I give you? Do you remember what kind of
Electron, I believe.
It was just the electrons, yeah. So so you're looking at radiation belt electrons if you're looking at that data, right? So so those can be challenging to interpret, and you may want to like scan backwards in time during a quiet time to see what they're doing, and then see if it changes. Okay, great. Solar wind. What's a challenge that you guys ran into, or a question you have?
So I think we, based on the proton data from ACE and Discover, as well as the bulk speed, and then also the magnetic data, I think we all agreed that we saw when we think the CME first arrived. However, there was later fluctuations in the data, later increases, that we had ideas for what might have caused those, but weren't entirely sure. We discussed that a little bit.
Okay, great. And then solar.
I think we ran into the issue where we were interested in what was going to happen afterwards, but in kind of the enclosed sphere of looking at just the solar data, we wanted to know. We already wanted to jump to the very end, so trying to
Great.
Yeah.
And so you're going to get to do that next. So yes, the ionosphere group has the problem of like, yeah, we see a lot going on, but what caused it? Because we don't know. You don't know what's down, what's coming in, and then you have the solar people have the opposite effect. It's like, we see something's happen, now what's going to happen later? And so you should be able to. So now you should start to be able to piece this jigsaw together. All right. I noticed a lot of people sharing their expertise, which is fabulous, right? You should absolutely be sharing what you're an expert in, and be generous with that. But I also will remind you that not everybody is an expert in what you're an expert in, and so one of the things you should be careful of is jargon and acronyms. So make sure that so first off, if somebody says and gives you an acronym or uses some jargon and you don't understand, it's not because you don't understand, it's because it hasn't been explained to you yet, right? So ask the question, right? Stop, slow people down and say, wait, I have no idea. You're talking about this thing KP. I have no idea what KP is. Can somebody explain KP to me? And so make sure you slow people down and ask the question. And also recognize, as an expert, you may be comfortable using jargon or using acronyms or using those things, and not everybody knows. And the way I often start when somebody asks me what is that is I start by the definition, right? And when it's particularly for an acronym, then you can just say the acronym is this, right? And so. And then give a way that maybe that thing is derived. All right. So just be aware of that as you're moving forward and you're discussing these things. Ask lots of questions of each other. I'll remind you again that this is really a warm-up exercise for the expert lecturers that are coming in, so that you are familiar with the whole system and you start to see some of as we start to take it apart for you with the expert lectures that will be coming in over the course of the next couple of weeks. All right, so what you should do now is go back into the synchronous groups, and each of you in your synchronous group should now have a piece of the puzzle that you can start to put together. And if for one reason you're missing a puzzle piece, let me know, and I will help you try and fill it. And between Mark and Christina and I will try and fill it in. All right. So Maggie, we got 9 breakout rooms open. Yep. Okay.
We
Great.
do. Yes.
So, if you remember which breakout your room you're in, if you can go back into there from the synchronous groups, and if you don't, ask us and we'll tell you. Oh, and Mark has reposted the synchronous groups again. Thank you, Mark. Have we lost people again?
Yeah, group 8 has 2.
Yeah. Okay, now maybe they've got 3.
Yeah, Trunali should be in group 3.
I moved her in there. I don't know if she has to accept.
Yeah, she physically needs to push the join button.
Yes.
Yeah, in group 8 is for Dorcas.
Yeah, I moved her in group 8 as well. Are you guys having any trouble joining your groups?
Yeah, so Brazil is an hour ahead of Eastern time. Okay.
All right. What my plan is right now, because it's always a little bit of a mystery with me, so I better tell people, is I'm going to take you through what I think was going on in this storm. And I'll certainly ask for Christina and Mark to jump in when they have opinions, and also ask anybody else to either ask questions or ask opinions. And so I've been adding to my presentation a little bit based on some of the discussion that we've been having. So the way that I want to do this, first I'll share my screen. Let's share that. Okay. So I put these sort of exercises together on a pretty regular basis, and I change things up depending on what kind of bug I feel at the moment, or I mean, after a while, I get tired of looking at the same storm, or something relevant shows up, right? So, and so I changed things up, and as I said, like I put this together like the night before last or something like that to so because I realized it was relevant and important. But the way I usually do this is the first thing I want to do before I go looking at for too much detail is I want to make sure it was geo-effective. So I think I think it was Dorcas that I was telling was looking at DST is cheating, because DST doesn't give you the whole story, but it certainly gives you the story. It certainly gives you a big part of the story. And DST is one of these magnetic indices that these magnetosphere physicists are fond of making up. And so there's an alphabet soup of, DST and KP, and is there another K index, Mark?
Yes,
AP.
every station has its own K index, and getting them all together is a planetary K index.
I see.
Which is semi-logarithmic, and so they have a linear KP, which is A or AP, et cetera, et cetera. And it's essentially looking at the range of fluctuations of the geomagnetic field at mid-latitudes.
Right, and then there's AP and AO and AE and blah 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 blah. So
the other thing though about DST, why it's cheating, is that if you don't have a response in DST, it's not a storm. The formal definition is a drop in DST. So
right. And what DST is measuring, it's it's ground-based magnetometers in the equatorial region, and that's telling you about what's happening to the ring current. So if the ring current is getting disturbed, and the ring current is part of the magnetosphere that is only around the equator and very close into the Earth, within a few Earth radii, and if that's getting disturbed, then it's, as Mark says, it's defined. That's how you define a storm. That's how the magnetosphere physicists define a geomagnetic storm. So I go check. The first thing I do is I go check DST, and I see if there's actually something magnetically important. So indeed, there was a storm that day. So now I know I can start going to look at the data. The other thing that I check almost immediately before I start spending a lot of time collecting other bits of data or links or looking at this is I also want to make sure that, so for this exercise, that all the groups have data to look at, something interesting to look at. And in particular, I find the most troublesome data to find is the ionosphere data. Within the last few years, I think this compiled TEC maps, and that stands for TEC stands for total electron current content. It has been very valuable to me because they're now compiled automatically, and these are based on the GPS, so GNSS data from known ground stations. So they look at the known ground station, you know where that one is, and then you look at where the GPS receiver thinks it is, and you say, aha, that difference must be the disturbance in the ionosphere, disturbing the radio signal coming from the GPS satellites. And there's something about dual frequency that I don't completely understand, and I don't think we need to go into. But the point is by looking at the disturbance in the radio signals that we now have, because we have this network of GPS satellites and these network of ground stations, we can then back out what the total electron content was through that that air column. So it's integrated over the whole air column. So you can sometimes see individual features, like some people were, I think I overheard people in the ionosphere group saying that they thought they saw the Appleton anomaly, this fountain effect. And I think that may be true around the so-called South Atlantic anomaly, which is really now the South American anomaly, because it's the Earth's magnetic field moves. But more importantly, we can start to see changes in this. The maps that I gave you to look at are absolute TEC. Another type of map that you could have gotten that's a little bit easier to interpret is the difference TEC. So it's taking the total electron content and subtracting that day from some kind of an average or a mean electron content. I'm not sure how that mean is calculated, whether it's over the last several days or it's something more complicated than that. But certainly what we can do is we can look at the disturbance from day to day. And you want to make sure that you're looking at local time. So in the ionosphere group, one of the group members actually had all the days lined up so that they could look across and compare all the maps at the same time. So that was a lot of work, and I appreciate that that kind of work got put in. But certainly, if we look at, so again, oftentimes my quick and dirty pass is just to look at two different days and see if I can see a significant change from one day to the next, to make sure that when I hand this over to participants in one of these workshops, and they look at the data, they've got something to look at. They've got something to chew on. And certainly what we see is that on the first here at noon, and then on the third at noon. So noon, this is noon UTC, so it's noon in England, right, on Greenwich Mean Time here and then here. So you're not too surprised that it's bright red in this region, because that's right where the sun is. You're getting a lot of photoionization. You're getting a lot of ion content, electron content throughout the whole thing. And then throughout the day side, you've got a lot of electron content. But you can start to compare from one day to the next. Certainly, it's a little bit redder over here. It's a little bit redder over Europe. What's interesting is while it's still like it hasn't sun hasn't risen in North America yet. There's also a positive storm effect there. So the ionosphere people talk about positive and negative storm effects. So you're getting stronger total electron content there, and then but also you can get negative storm effects because you've got these recombination rates. So it looks to me like in South Africa and in Antarctica, right, where it's summer, right, because the date, it's February, so it's summer in the southern hemisphere. You're going to get these negative storm effects where you're getting higher rates of recombination, and so you're losing ions and electrons there and there. So, and as Mark puts it, yes, the change in the number of electrons is the source minus the loss plus any transport. So, and this is, I think that's that's where I start to like lose it with the ionosphere. I can't grok the whole ionosphere, because just when I got just when I think I've got my my brain around something, you know, I talked to an ionosphere physicist and they said, but you've forgotten about the anomalous recombination effects due to the winter anomaly in the southern hemisphere on Tuesdays when it's cloudy out. I'm like, yeah, okay, never mind. But there are smart people who are able to do this. What I find really funky in these maps is I like these tracks. I think, my guess, I don't know exactly what that is, but my guess is that is an orbiting, that's a satellite orbit of some sort. It looks like a satellite orbit of some sort. And my guess is it might be a GPS receiver on a spacecraft, but I don't know. So I don't know if Mark or Christina have any insights into that. You don't have to say anything if you don't.
Yeah, so there is thousands of ground-based GPS receivers, and most LEO satellites now have GPS receivers, but you need to have that dual frequency GPS receiver. So the swarms have it, as well as Cosmic, which is there's two of them now, and they're able to do not only point, but occultation, which is sort of looking at a limb scan. And then there's satellites like Swarm and DMSP that actually have density data. So they can intermix both real density data with TEC data sometimes on plots like that.
Okay. Interesting. All right. Great. Questions on the ionosphere data and what you would have been seeing? Or comments?
What would you expect to happen in the ionosphere in the aftermath of a storm? Nick talked about these positive and negative effects. Is that what you expect for all the storms and for the ionospheric? Yeah.
Well, I'm not sure in terms of electron data, but I would anticipate enhanced auroral emission in the geomagnetic north and south for enhanced solar activity.
Yep. And that when you think about any of your domains, think about sort of what the parameters that are used to describe it. And so for the ionosphere density, and that could be a function of latitude, longitude, and altitude is important. And that contributes to conductivities and all types of things. But one of the problems is that you can get different responses at different places for the same event, and they actually could be happening at very different times. A flare, you'll see the EUV hit the day side of the Earth in 8 minutes. The night side has no idea that you just got blasted. So there's going to be day-night asymmetries. And then when you couple energy into the ionosphere, you're coupling it into generally the high latitudes. And then you can have propagation of those effects away from that. So there's time delays due to propagation effects, and there are some time constants to the system. So there's a lot of complications that can happen. And as this figure shows, at essentially the same local time in the American sector, depending on your longitude, you have a different effect. You have this decrease or a negative phase and an increase, a positive phase. So your latitude and longitude local time is very important.
Yep. I went looking for auroral effects, both there were, and they've disappeared now, but there were catalogs of people taking auroral pictures. I think spaceweather.com has ceased supporting their auroral catalog. I don't know why. And then there's also a polar orbiting satellite, DSMP, which does regularly take auroral pictures. And I didn't see, so I would have given those to you, but I didn't see anything like really compelling in them there wasn't any large there wasn't a large effect. So I think the large effect was the general disturbance of the ionosphere rather than the auroral. There wasn't a strong auroral component to this. DMSP. Thank you, Mark, for clarifying my acronyms. So great. All right. Let's move on. Okay, so now we got to figure out what happened. So now I know what I'm looking for. So now I want to see what the drivers are, right? And so here's the solar wind data. And I think this is where we really get our first significant mystery here. Certainly, I think what people identified is there's a shock impacting. So this is from the ACE spacecraft and the Discover spacecraft. Both are at L1. They're about 1 million miles upstream at the L1 point. So that's which is about 1% closer to the Earth, to the sun than we are. That at typical solar wind speeds, that gives us about 45 minutes of warning before we know something's going to happen, right? Oh, by the way, Mark said you've got 8-minute response times for the solar flare, and which yes, the sun is 8 minutes from us, and I'm not saying, and Mark knows this, of course, but just keep in mind that 8 minutes happened already by the time we see the solar flare, right? You see the X-rays, and you know, if you're at the Space Weather Forecasting Center, you see the X-rays and you go, oh, that happened, right? And so then things are already going on, and so then you go to start sending out your alerts, so because it's speed of light. So but for the solar wind, you have a little bit of lag time. We get the radio communications from the satellites prior to the solar wind arriving. So we've got a shock here, accompanied by a sudden increase in speed, right? So an increase in density and an increase in speed is a indication of a shock. Fast wind is catching up. Sorry, fast wind, I guess. Well, this is time, so I can't point to it right. Fast wind is catching up to slow wind. It starts to pile up, and you get a little bit of a shock. The increase in speed is like 400 to 500 kilometers. So this is a very mild shock. It's not very shocking, as it were. What's the people struggle with this a little bit? What's the confusion? What's the confusing part about this? I'll open it up to anybody.
Go ahead and either raise your hand or just unmute yourself or type in the chat.
Yeah, thank you.
It seems like there's 2 shocks in the velocity, but only 1 shock in the density.
Oh, that's certainly true. So you're looking at this shock here on the third?
Yeah, that's right.
Yeah, okay. So one change in velocity here, one change in velocity here.
How do you know it's a shock?
Huh?
How do you know it's a shock?
Oh, I don't.
Just asking, yeah.
I mean, there's certainly something funky going on with the density here, and ACE is saying one thing, but that's well away from this, so it's not, yeah. So
traditionally, shocks are defined by the magnetic field
okay.
compression, right? So usually, it also is often associated with, a compression, a jump in the velocity and a jump in the density, because you're having a compression there. But generally, it's the magnetic field that defines whether it's a shock or not.
So there's a clear one here just before the second.
Yep.
What's the other confusing bit? So, Kushik, I thought your group was working on this.
Yes, actually the confusing part comes when we try to connect this with the NLIL model outputs simulations. So that showed the passage of a CME that crosses the Earth on 1st of February, but we don't see anything happening on the 3rd of February.
Right. So you're saying this guy right here is the question mark.
Yes.
Right. I don't have a good answer for that because it seems pretty far away from when the shock front of the CME would cross this to sort of say that that's the flux rope. It's a day away. So I don't know if anybody else has any insights into that.
Yeah, so if you are looking at sort of the total B compressions, you have those two, that first one on the second, and then the one you're pointing to on the third. So that is a full day. And a day is essentially something going 800 kilometers per second to go 1 AU. So it's half an AU type of thing. So that would be a pretty big structure. But could there have been multiple events on the sun that essentially you're seeing two things happening, but they're just essentially part of the same structure? So there's all different types of potential confounding issues.
So that second structure there, that's, whoops, disappeared. That's clearly a flux rope, right? You see a clear rotation in the magnetic field. You don't always see flux ropes associated with every CME. I agree that there's not a clear shock ahead of that flux rope. Usually you have a shock and then a sheath region, which can be kind of substantial. A day, I think, is on the edge of what you would, kind of think is typical or something. I think that's considered very long. But keep in mind that you may not be seeing the rotation of the flux rope exactly when you enter the CME, because depending on where the turns are and where you're crossing through the CME, you may or may not see it, right? You could be only seeing the flux rope on a flank of the CME or various different things that happen. So I'd be hesitant. I agree that they're separated by a lot, but I'd be hesitant not to call them part of the same, event that left the sun kind of thing. The other thing you can have happen is you can have a CME that goes off really fast and then slows down a lot as it goes to 1 AU. And the shock it's driving is going faster. And so it can separate, you can get a bigger distance as it propagates to L1 between the shock that was initially, sort of, you could think of it as a what's the word I want? Sort of a piston thing that goes off and creates a very big shock, and then that propagates out, and then the rest of the piston sort of slows down behind it, and that will make a bigger gap between when you observe the shock and when you observe the actual flux rope behind it. So I agree that those delays are pretty big, but I'm not sure I would immediately jump to saying that there's two different events here.
Okay. Christina, could you point to me? I know that there's this thing called a rotation. I've never been very good at looking at magnetic field data and going, oh yeah, that's rotating. Would you?
Right. So what you're seeing is, it's kind of small on my screen, but what you're seeing here, this is the rotation. So if you look at the orange one, which I think is the tangential component of the magnetic field.
It's BZ.
Oh, is that BZ? I can't see it from here. Okay, so
and the red one is B total.
Okay, so what you want to look at is So there's different ways of plotting this that are easier to see. A lot of times people, instead of doing an RTN coordinate system, they actually calculate a theta phi. They go into a spherical coordinate system, right? So you can see a theta phi coordinates, but you know, it's all the same, you know, it's just how you look at it. But in particular here, what I'm looking at is this change, dramatic change from basically positive values to negative values. So what you're seeing is a rotation of the magnetic field going from, if that's Z, it's going from pointing up to pointing down, basically. And so what you're seeing is the spacecraft is sort of following this thing, you know, and at one point it's, you know, the magnetic field is this way, and then it slowly rotates as you go through the structure. So what you're seeing is one component of a helical structure, and you're seeing that basically rotate. That's why it's a lot of times it's easier to see in the theta phi, because you can more easily vision it as a, you know, a helix. But if you look at the other components, sometimes you see rotations in those components, sometimes you don't. So it's not like it has to be in the Z component or the T component or the N component. It might be a combination of them, but this kind of effect where you see this big long diagonal here is the strong signature that you're seeing. Does that make it more clear?
Yes, thank you. Andrea?
Andrea's got a question.
Oh, okay.
A lot of questions.
Well, I'm not sure if you mentioned this already or not, but what you just described, would that be considered a current sheet crossing?
No. So a current sheet crossing, so you can get a current sheet crossing, which is the change in the magnetic field going from positive to negative, but it's usually a very abrupt thing. It goes from, I wish I had an example, but it'll be positive and then it'll drop negative over a pretty quick thing. What you're seeing here is a more gradual rotation. You know, this is half a day. So what you're looking at is you're going through a much bigger structure and you're seeing a very smooth rotation. It's not an abrupt change. And usually you see it in, like I said, sometimes you see it in multiple components, whereas current sheet crossing is going to be basically just BZ. It's going to just change from one polarity to the next. Or sorry, not BZ, BR.
BR, yep.
Yeah, sorry, my bad. So that's the other thing, is this is the Z component, not necessarily a BR component. Because a current sheet, remember, you're going from the side of the sun where the magnetic field is coming out in its polarity to the other side where it's coming back in. So you're seeing a switch in the R component, whereas this is a switch in the Z component. You can see that the R component, I think, is, what did you say that was red? Is not really
the red
changing.
is the total.
Okay, so I don't know where R is in there, but usually R is the large part of the component, but just it's a little small on my screen, so
yeah, so
I'm
yeah,
trying to read it. Yeah,
And,
no,
and
it's
yeah, you can have it in spherical coordinates, so BR, and so Carol's talk and the all the equations showing the IMF were BR and B theta and B phi, but we could also be in Cartesian, BX, BY, BZ, and so for the Earth we like Z, the Z component because of the Earth, but that's the theta component.
right.
if you imagine a
BX
helmet
is
stream,
basically BR, right?
and BX is BR in GSE coordinates.
Right.
If you imagine that helmet streamer, so you have a dipole field line and that comes out and there's a long current sheet going out into interplanetary space. On one side of the current sheet, the field's going back to the sun, and on the other side, it's going away from the sun. So we have this towards and away sector. So as that current sheet flops, as the sun rotates, the Earth pops above and below it. And so you can often see that every 14 days you pop up and below, but of course you can have more complicated geometries during solar maximum, so you can have multiple current sheet crossings every rotation.
Sarah.
Thank you for clarifying, Christina. That was super helpful. One question I had for you that you briefly mentioned. So you said some CMEs can kind of erupt off the sun very quickly and then get slowed down by the time they hit 1 AU. And I was just wondering what slows them down.
So the most obvious thing that slows them down is they're usually going much faster, not always, but they're usually going faster than the solar wind ahead of them. And so you can think of that as it's running into a density. I mean, the densities are all really low, right? But it's a magnetic structure that's running into a plasma ahead of it, which also has a magnetic field and it has a density. And so it's sort of running into this thing, but it's gonna, and that's what's creating the shock. But in doing all that, it's also being decelerated, right? So you will notice, so if you actually make these calculations, it's kind of interesting. If you have a good measure of from like say LASCO of the CME and how fast it's moving, keep in mind that's a speed really close to the sun. And then a lot of times people will calculate, they'll find out, like, you know, in this case, I'm going to try and annotate this thing again. In this case, whoops, sorry. My annotation skills are questionable, but in this case, when the shock,
want me to bring up a bigger version?
Sure. So in this case, when the shock or the CME arrives at 1 AU and you say that's related to the CME that left the sun, you can actually calculate that time difference, and you can say, okay, you know, how long did it take to get from the sun to the earth? And you can calculate an average velocity, and you will almost always find that average velocity is actually significantly less than the velocity of the CME when it left the sun. And that's because it is slowing down along the way. Sometimes they can actually see it in the LASCO data if they plot what they call a time height profile, where they plot the height of the CME as a function of time, and then if it's going at a constant velocity, it would be a nice straight line, but sometimes it's not a nice straight line and they can actually see a curve. And so if you then fit a polynomial to it, that gives you an acceleration. And so if you see it do something like this, where it curves over, then you know it's decelerating. They don't always decelerate within the field of view of LASCO, because that's just, you know, several solar radii, not all the way to 1 AU, but sometimes you can even see it there. So generally, it's just that it's running into denser, you know, slower solar wind in front of it, which is going to slow it down. But it's also going to be what drives the shock, if that makes sense.
Yes, that makes a ton of sense. Thank you for clarifying.
Yeah, sure.
Ashutosh.
I agree with Christina that it seems very difficult to me to think that these events on 2nd and 3rd February are two different CMEs rather than being part of one, because first of all, what I see is there is along with the rotation in the VZ component, there is a hike in total intensity. But for the 2nd February event, we don't see any hike in total intensity, which makes me doubt if it's another CME. That's one comment on that. So I have two questions. One is, what exactly do we see in this magnetometer data in case there are actually two CMEs? So when we are completely sure that there are two CMEs, how will this data look? That is one question. And second is, I was interested to know how the say plasma beta, that parameter will change when the ICME, this interacts with the magnetosphere.
Okay, so I'm going to answer the first part and then throw it to Mark for the second part. So basically, what you normally see for a simple, nice, clean event is, right, you see, you know, your magnetic field, you see the shock goes up, and then often it kind of declines, you know, like this. If you have and which is sort of what you're seeing here, if you also have a magnetic cloud in there or a flux rope in there, if you look at the components of it, you'll see that some of the components will also have a shock, but what you'll see is they'll have a rotation you know, something like this in certain components. And so I believe that that's what's going on here in this thing. This is a rotation. So that's probably in the magnetic field. My guess is that this is sort of a very complicated evolving structure. And it does bother me a little bit that there's this gap here. But what you also have to keep in mind is that these structures, generally as they're going from the sun to 1AU, they're expanding, right? And so what you can actually have is an increase in the magnetic field at the back side of the flux rope. Because of the way it's expanding, it's actually sort of putting pressure in both directions. And so you can actually get a pileup of the magnetic field on this side. I'm not sure what also you can have is, and you can't tell it from the magnetic field data, but the question is, you know, what is the solar wind stream speed that's going on in this section, right? If you have a fast solar wind stream that's coming up behind the CME, it can also cause sort of some compression that's going on the backside. So there's lots of different things that can kind of be a behavior here that's causing all these different structures. I don't really know how to explain why there's a you know, this distance here between what is pretty clearly a shock here and then this decrease, and then it gets kind of smooth. Usually what you see is also sometimes in this region between the shock and the rotation, you can get what's called a sheath region, where this can get really noisy. So you get magnetic field just fluctuating all over the place. And then when you go into the magnetic cloud, it gets kind of smooth. And so in that case, you would see, boy, I don't know if I can erase some things. Let's see. I can erase, whoops, too much. Okay. But basically in that case, you would see, you know, your shock come in, a bunch of stuff, and then you'd go into the magnetic cloud. And so your component might go up and do a bunch of things, and it may not start to do a nice rotation until here. So, you know, there's various different ways that this can kind of manifest itself. And this shock region, I'm sorry, this sheath region is basically that separation between the shock that's driven in front of the CME and the flux rope or the actual CME that's sort of pushing it along. So in terms of plasma beta, I'm going to hand it to Mark, who's actually below me in my display. And so you can talk about that, the plasma beta gets affected when it actually hits the magnetosphere.
Thank you.
Yeah, so to add to complications, you know, not only is there evolution in transit, so things can be expanding. So you'll see those types of, there can be things in the way that had left the sun beforehand. It could be running into a co-rotating interaction region or having one behind it. And so, you know, it looks on one panel like there's one big event, but it actually could be sort of a merger. And sometimes you
so
can
Mark, do you
off.
want to explain what a co-rotating interaction region is? Because everybody may not know what that means.
Yep. So there's a number of sort of events that come off, and Nick had described it a little bit already in the sense of a different speed solar wind, and there's the solar wind's primarily bimodal, fast solar wind coming from coronal holes and slow solar winds coming from closed field regions, and a lot of debate on the origin of the slow solar wind, and but they can run into each other. Essentially, if you're going 600 kilometers a second, and as I rotate around, as this Enlil model shows, the solar wind is going out radially. So as the sun rotates, there's going to be a new parcel coming out in that same azimuth direction, and it's just going to start piling up. So that's a CIR, and you often will see this compression and changes in the magnetic field as you go across that interface. So you could have a CME blasting into these sort of standing co-rotating spiral patterns, and then you get something funky depending on when it left the sun and its relative location with the longitude of the coronal hole.
Yeah, and in
Um,
fact, you can even see this effect in this animation here, right? So when you watch this CME that's going to come out right here, you can see it doesn't stay circular, right? It propagates differently on this side than it does on this side. And that's because one part of it is running into this green section and the other part of it is running into this blue section. And those are different solar wind speeds. So when it's running into the fast solar wind, it's able to go faster without slowing down. When it runs into the blue section, which is the slower solar wind, it gets kind of pushed back. So you'll see that it kind of distorts in this direction.
And was the question on plasma beta of what is it when it hits the Earth, or a more general question of how it evolves from the sun?
And when it hits the Earth, how does it change in the in situ measurements?
Yep. So remember, Carol defined its plasma beta NKT over B squared over 2 mu naught. So the ideal gas law pressure over magnetic pressure. And it's a dimensionless number. And it essentially anything bigger than 1 says that the plasma pressure dominates, and anything smaller than 1, the magnetic field dominates. So you can sort of which pressure is controlling the motion and structure of a magnetized plasma. For high plasma beta, it's the plasma that's pulling the magnetic field with it. And when it's a low plasma beta, the magnetic field is essentially confining all of the plasma. And so when it hits the Earth, the typical solar wind, the plasma beta is about =1. They're very small. And if you look at the total pressure in the solar wind, the one that dominates is actually one that's not in beta, it's the ram pressure. So if you sort of think of the total pressure of the solar wind, you have the ram pressure, the pressure of motion, the rho v squared, and then you have your NKT, and then you have your B squared. Rho v squared is like 99% of all the solar wind pressure. So the kinematics, the dynamics of the motion usually dominates most of the plasma physics that's going on.
So I'm going to use Miguel's question to sort of move us along, and because I think that this is a fine example of exactly what we think is going on. But then I'll also have a cautionary tale about the models here. So Miguel is asking what the if the CME can modify the CIR. Absolutely, and that's exactly what you're seeing. So the CME and this goes back to what Christina is saying, is that the CME. So these are constructs that we have in our brain. That CME is that we make up, right? We call this thing a CME. It's really just a burp of plasma that now is in the solar wind and interacting with it. We can talk about like different populations that are moving at different speeds and with different densities, but it's it's starting to just add itself to the plasma, and it gets modified that way. So yes, absolutely, the CIR is impacted by the CME. You'll notice in particular that even without, in this model, there's no magnetic flux rope in that CME. It's just going and modifying the plasma. It's just a density, an extra density, and extra velocity that's being dropped into the model, and it's still modifying the connectivity of the magnetic field. So it's still modifying magnetic field lines and pushing them out. So so yes, those things can modify each other. Let me give you a little cautionary tale about looking at these models. Remember, the map is not the territory, right? The model is some guess that we have about what physics goes into this this material, and The way that they put CMEs in here is really not very elegant at all. In this model, and I'll talk about this more tomorrow, I'll give a short introduction to solar and CME and solar wind modeling. But this model is runs the solar wind model runs pretty continuously and more or less automated. But if you want to put a CME in there, somebody's got to go look at the coronagraphs, say, hey, there's a CME, and it's one I'm interested in. Figure out the parameters, how big it is, make some guesses about how, well, they can figure out how fast it is based on what Christina was saying by measuring the speed as it moves through the coronagraph. Figure out what its density might be, and then by hand go into this model and put in the density, extra density, and the extra velocity, and then let it evolve. So if there was another CME that maybe wasn't added to this, you're not going to see it in the model, okay, because it has to be done by hand. Also, as I was saying, we don't yet have a good way of guessing even what the magnetic field is that's wrapped up in there to be able to model it. So that's an area of current research, and there are groups trying to do it right now, but we don't have that's not something that we can do on a regular basis. Right. So that's my cautionary tale about models. Let's see, do we have any other questions? Oh, SEPs can be generated by the, SEPs can be generated by the shock. I didn't spend a lot of time talking about the SEPs that are here. I gave you the, interestingly enough, I didn't see a lot of SEPs in the ACE data, so I didn't give that to you. I saw them more in the GOES data. I think that's because the area that went off was top dead center. It was zero longitude. And so magnetically, we weren't connected to the to that area, right? So you'll know. So if the area is here, that where it was launched from, then the magnetic fields that the energetic particles will be following are going to be swinging away from us, and we won't see much of them. So I think that's where the solar energetic particles, we don't see a lot of solar energetic particles from that. All right. I'm going to move on because our time is slowly running out. So we looked at DST, KP, and I'll show you KP in a minute. So that the magnetosphere data, that was the extent of the magnetosphere data. In other versions of this, I give people ground-based magnetometers, but I think I wanted to keep this simple. The models are interesting. And again, you should be aware of how these models are run. Basically, to run the magnetosphere models, they take data from the ACE spacecraft, the plasma density, the velocity, and the magnetic field strength, and they just paste it onto the front of this model. That's their sort of inner bound or their outer boundary condition. And there's more details that we'll talk about later on in the course in the week about how these models work. But then and then you start just feeding that in, and the solar wind blows in that way and pushes the Earth's magnetosphere in, compresses it on the day side, extends it on the night side. This is about halfway through. Well, it's a little ways through the storm, and you could start. I think this is evidence of a reconnection happening in the tail. You've got what are now solar wind field lines that are disconnecting from the tail, and so you've got these snapping out, and then these snapping back, bringing plasma with them in a reconnection form and bringing it into the inner magnetosphere and ultimately dumping it into the auroral regions. The other thing to notice is this is somewhat before the shock front hits on the first, at the end of the first, when the shock front hits. And you can see this line here shows the magnetopause, and where the magnetic field of the Earth and the sun sort of meet up, or the solar wind rather meet up, and so this is where the magnetic field of the Earth takes over as you go inside the Earth's magnetosphere. Notice that the magnetopause within a couple of hours gets significantly compressed, and is now pushed into close to geo. It's probably about eight Earth radii in on that. So so now we know that we're not quite getting to expose any of the geostationary satellites to the solar wind, but it's starting to get close, and people are starting to get worried a little bit. All right, let's see. Comments. Curious about the spike in the GOES X-ray observations.
Okay, I was in the process of typing a very long email explaining or chat message about that. I'll just quickly say it because I can say it a lot faster.
Well, here, let me pull up the GOES data for you.
Sure. So one thing you have to be aware of with the GOES data is that these X-rays, these monitors, are responding to X-rays that are happening anywhere on the surface of the sun that it can see. So just because you have a series of these doesn't actually even mean that they're coming from the same location. And that's actually one of the reasons why GOES has upgraded and created an X-ray imager of the sun that they now have on the later spacecraft, so they can actually image where these X-rays are coming from. But from a plot like this, you can't actually tell whether these guys are all coming from the same active region or not. That said, so I assume you're sort of talking about these guys in relationship to this guy and all these other spikes. And so an active region can be popping off all kinds of, emission of X-rays all over the place. And they can be short and they can be very long, and they have different characteristics about the magnetic fields that are involved in terms of what you're really seeing here in X-rays. And so these are real flares. Generally, if you're going to have SEPs or a CME go off, you generally have something that looks more like this guy, what we call a long duration or a longer duration flare, where it actually exists for several hours as opposed to these short ones. You can have small CMEs that go off with these things, but they're generally not the big things that are driving a big shock that's going to accelerate a lot of particles. So while these guys are real and they're probably indication of activity, if you're looking for something that's going to drive a space weather event or a geomagnetic storm, you're looking for something that looks much more like this. Hopefully that answers the question.
And like most observables, not every flare generates a CME, and not every CME has a clearly identified flare associated with it. And as you can see here, there are a lot more flares of various intensities than there are CMEs.
The other thing that you'll also run into, so there's always more flares than there are CMEs, but the other thing you'll run into is that you can see a CME because of the way LASCO works, going off, off to the sides or even backwards, because of you're looking at sort of a projection. You can only see these X-rays really if they are on the front side of the sun. So you can have a region that's creating X-rays and a CME and not actually, I'm just going to use for an example, this time period here where it's relatively quiet, but you could actually have an active region on the back that created a CME, for instance, that you would actually see, but you wouldn't be able to identify what the X-ray is that associated with that. So there's all these kind of complications about where things are going off and what we can and what we can't see.
And purists call CMEs things that you see in LASCO, sort of coronagraph stuff, and ICMEs, interplanetary coronal mass ejections, are the signatures in the plasma and magnetic field you see at ACE or wind or something in the solar wind. And we're almost sure they're the same thing because
There's actually a movement to stop using ICME because it's just confusing.
It's the same thing, damn it.
It's just the same thing. So just leave it alone. Just call it CME.
It's a movement because they have like placards and
yeah,
and,
they said drop the
stickers.
eye, drop the eye. No, I just
Yeah. And it's this, there was a debate with plasmoid and flux rope because plasmoid
Yeah.
were technically two-dimensional structures, but they're the same
Yeah.
thing.
This is, yeah, I should tell her, you're going to run into this in pretty much every field. We have this in SCP's solar energetic particle data. There's things that are given different names, but are essentially the same sort of thing. And part of that, a lot of that is historical because of how they were observed initially. And so, you know, before we made connections between these things, they were sort of called something, you know, to identify it, which only later they said, oh, that's actually the same thing as what we're seeing over here. So a lot of that nomenclature hangs around and is just confusing, but we keep it around.
One quick note on units. Unfortunately, the way this is plotted, it wasn't as clear what the units were. This is the units for X-ray flux are like any other light flux are watts per square meter. This is a log scale. The N stands for nano and the mu stands for micro, right? So this is really 10 microwatts per square meter. So 10, which is 10 times 10 to the minus 5, 10 times 10 to the minus 6, which is 10 to the minus 5, right? So this is this guy just peeks his nose up above the 10 to the minus 5 line, which officially makes it an M-class flare. If you look on the categorization chart. All right. So, so I know there was some confusion about the classification of that, and I'm sorry that the units weren't made as clear on this as possible. So, so it's a flare, and it's even an interesting flare, but it's just barely interesting. It's sort of like, yeah, it's, you know, kind of interesting flare. Let's see, can I move? Why can't I move? I want to stop drawing. There we go. There we go. All right. Just quickly on the solar data, right? So we've got sunspots. Notice that not every magnetically interesting region has a sunspot associated with it. So here and even here. Well, here we've got the plages that might be indicative of something, but we've got, you know, magnetically active regions that don't have sunspots, and they're active in the EUV as well. This looks like the candidate for that flare that Christina was circling as probably the one that sends off the CME, and certainly this is what I was saying about it being top dead center, right? So magnetically, any magnetic field lines that are near this, that are coming out towards Earth, are going to follow the Parker spiral and turn away from us. So the high energy but low density particles that are going to follow those field lines are going to veer off, right? But the CME is going to come straight at us, and it's better to look at this in the coronagraph images. Before I do that, I want to remind you that I'm giving you both the L1 coronagraphs from SOHO. Sorry.
SOHO.
Yeah, and so the L1 coronagraphs from SOHO, which are essentially at Earth, they're looking sunwards. But I'm also giving you the stereo A coronagraph, which doesn't give us too much more information because it's only, I don't know, about 30 degrees off of Earth's line. So when we look at those coronagraphs, blow that up, right? And we scroll through here. These are easy to see, and if you just take images, they're hard to see, but they're easier to see in motion, and so you can see around here a halo coming out of this coronagraph. And again, for stereo, since stereo is nearly on the same, is very close to us, it's also a halo. Right, so it's all, if you look at it, I mean, there's a strong region on the right, but if it seems to be all around this. So a halo CME essentially is doing this, right? All it's doing is getting bigger as it moves out, right? And so it's as it's moving towards us, it's just getting bigger and bigger and bigger. So we perceive that as moving out from the sun, but it's really moving directly towards us, rather than coming off on as an object shooting off to the right, which you will see later on. So on the, I thought you'd see, oh, there it is, yeah. So that's they refer to this as a light bulb CME, right? Because it looks like a light bulb. And in fact, I think I see remnants of a flux rope in there, but I'm not sure what that could be my own mind making things up. So right, so that is most of what I wanted to show you from this. We want to wrap up soon, and I need to give you a little bit of an assignment. I'm going to stop sharing that screen. I want to show you one more thing from this event. Here it is. All right. So this is a presentation from Sue Fang from the Space Weather Prediction Center. Come on. Yeah, there we go. All right. So just to give proper credit, she, along with a number of colleagues, are working with people at SpaceX. Of course, SpaceX was very concerned about losing the large number of spacecraft that they did. And I could talk a little bit more about what they were trying to do. But the challenge has to do with satellite drag. Oh, I forgot to ask this question. I'm going to go here and share my screen one more time. So here's the question. So when you get a geomagnetic storm, along with the solar forcing that you may have as background, you're also going to get energy deposited by particles precipitating in from the magnetosphere. And so you're going to heat the upper atmosphere. You're going to heat the thermosphere. The thermosphere and the ionosphere cohabitate together, right? They're two different populations of particles in the same location. And you're going to heat the thermosphere. So you're going to heat all the neutral atoms, which are the majority. That provides most of the density of particles in that region. The ionosphere is, I won't say along for the ride because it has significant effects, but much less dense. The physical mass of the ions is much smaller than the total amount of the neutrals. If I heat the thermosphere, what's going to happen to the density at a given altitude? So I'm at, let's say, 130 kilometers, picking at random because Starlink, right? that's where they launch to in their first, as part of their first phase, and then they boost to a higher orbit. So they're at 130 kilometers. I now heat the thermosphere. Does the thermosphere get more dense, less dense, or does the density stay the same? And you can use the stamp features on your annotate button to indicate what you think is happening. So you should be able to go to annotate, get a stamp like question mark.
You can also just guess. If you're not sure, just pick one.
Just pick one. I'm more curious as to what people think. Okay, so we got lots of takers. We got some takers for higher density, lots of takers for lower density. Nobody like stays the same, huh? Can't sell any stays the same. So I'm not, Hasna, I'm not talking about the ionization. I'm talking about the temperature, yeah, of the so I'm talking about the temperature of the thermosphere. So okay, great. This is a little bit of a challenge. This is counterintuitive. On Earth, if I take a balloon and I hold it out in the sunlight and it heats up, it's going to expand. Okay, and because PV equals nRT, I'm raising the temperature. I'm keeping I'm not keeping the volume the same, but the volume's and the pressure stays the same. So the volume's got to go up. In the upper atmosphere, in the atmosphere in general, but the upper atmosphere in particular, what happens is the whole atmosphere is going to expand, which means that lower altitude, higher density air is going to puff up and going to come up to a higher altitude. So at a fixed altitude, you're actually going to increase the density. All right. And so that's a little I think that's a little counterintuitive. I'm trying to get out of this presentation. There we go. But it's important when you're considering satellite drag, because that means during disturbed times, you're more likely to get more satellite drag especially at low altitudes in low Earth orbit. Things like geosynchronous orbit, you don't have to worry about satellite drag, or if you worry about it at all, it's not very important. All right, 2A wanted me to. I asked if I could share this presentation. She said yes, that's fine, but she wanted me to point out that this is material that is being prepared with her colleagues at SWPC and along with I think some people at SpaceX for publication in Space Weather, and so expect to see this full story in Space Weather at some point in time. And here is what she wanted to. There's just a few things I want to show in here. So first off, something to keep in mind is that at the same time that you're getting an increase in the magnetosphere index, the KP index here in red, we're also getting an increase in the 2-day average of F10.7, which is a proxy for the UV flux. So you're getting more heating into the upper atmosphere at the same time that you're getting what amounts to a fairly minor storm, because the KP values, for those who looked at it, are very small. Here, there's a better, here is probably a cleaner plot of the solar wind measurements, but they, we already saw this. Here's the shock, and then here's the rotation that Christina was talking about, and then the KP value are plotted down here. And you can see for a couple, so these are KP is a 3-hour average, so each of these blocks is 3 hours. So there's a 6-hour period here where it's up to like close to KP6, and another 6-hour period here. This is the 6-hour period that's important, because this is when the launch happened, and this is a minor storm as far as anybody's concerned. There's not a lot going on here. But the important thing that does go on is here is the modeling, and this is where modeling can really shine, especially if it's done correctly and you trust the model, is you can get a global picture of what's happening. And so the modeling of the ionosphere and the thermosphere together allows you to get a picture of what's happening to the neutral densities. And it's the, I'm going to go full screen here. View, can I go to full screen? All right, I'm just going to zoom in. And I'm going to zoom in once more. All right, so here's the density of the neutral densities at 210 kilometers. And more importantly, this is the anomalous density. And you can see that overall, you've got these patches where you can get a much higher density. You've only got a lower density here, but everything else is either normal density or slightly higher, up to 20%, it looks like. Maybe up to 40%. And we can go to an overall average, a global mean neutral density change for that is shown here. And this is comparing two different models. The EMSIS model, which is what SpaceX was using, and then the WAM model, which is now the state-of-the-art at the Space Weather Prediction Center. I don't know, well, EMSIS, I think, stands for something molecular spectroscopy and incoherent scattering, right? So it's a combination of a couple of techniques, and it's an empirical model. I believe the WAM model is also an empirical model, but it's much more detailed, and there's a few other details that are going on. But you can see that there's a significant change. Note this is on a log scale. There's a significant change in the density at any given altitude. So these two are pretty well separated. And the problem was, it was at these altitudes that they started trying to maneuver the spacecraft, and then because of the satellite drag, they lost control of the spacecraft. So it wasn't that they deorbited because of satellite drag, but the spacecraft started to tumble, and they couldn't get them back into control again. So my final sort of conclusion is, we like to say in New England that we're having some weather, right? And which I always find amusing, because we're always having weather. It's what kind of weather that you're having is important. But we're always having space weather. We're always having some space weather. The space weather events are happening on a regular basis. The space environment is variable. Even moderate storms can cause impacts, especially when you're operating at the margins, right? When you're operating in particularly clever ways. Okay, so we're nearly out of our time, but let's take we can take one or two questions or clarifications from anybody who is who's on. And I'll stop sharing. Oh, did I get that? I got the conversion, I got the units wrong. Thank you, Miguel. Yeah, they did something different, right? So, okay. All right. We asked, as a sort of the last thing I want to share with you is we asked the various speakers who are going to join us for some, if they had any particular reading, particularly from the Carl Schreiber's text, that they would like you to do. And about like 75% of them gave us radio silence. So, but then the other 25% were like, oh yeah, you should read the whole thing. So we tried to get them to be more specific. And Mark Chun was one of the people. So Mark will be talking tomorrow on solar data. And so we're gonna go into more depth on some of the stuff that I skimmed over near the very end there. What he suggested, I'm going to put this in your time zone group work, was, so let's see, I'm going to, yeah, there we go. So, so he wants you to look on, in Principles of Heliophysics, he wants you to look more at magnetohydrodynamics, so chapter 3. I think that's what's in chapter 3. And so I'm suggesting that you've already looked at chapter 3.1 and 3.2 for Carl, and so you can look at 3.3 and 3.4, and then he wants you to look at sections in chapters, one section in chapter 6. There's also the link to another online text by Dr. Basari, and I'm suggesting it's a general text, and it's conceptual, so it is pretty easy reading, but he was suggesting a significant number of it. So I pulled out a few sections here that you might want to look at, so as preparation for that. Some of that we've already either covered in the reading from that you did as pre-reading. Some of it is we covered today in the discussion of this problem, looking at various data sets. So you may find that it's a good review. All right. So that's in the time zone work, and you will take some time if you want. The readings are posted in the Slack time zone work channel. Yes, thank you, Maggie. And so if you want, get together as a group and review some of that for tomorrow. That might help you focus your studying. Questions on that? Going once, going twice. Okay, well, we'll see you all tomorrow then, unless, sorry, Mark or Christina, do you have any last comments? Okay, great. Then we'll see you all tomorrow, and have a good morning, night, evening. Bye.